Okay, thank you very much for coming. It's always a great pleasure to be in Toronto because it has been my home many years ago. So it's always a pleasure to be back. So today, as John said, we talk about Maxwell Demon. First, let me just mention that this is not the only kind of research I do at the moment. So I will just briefly review this because if you're interested in other topics, you may want to contact me via email. So most of my research is on classical and quantum nonlinear optics. These are two results of this year, one on generation of hyperentangled state and one on frequency conversion in silicon nitride. I also study light matter in general, in particular developing approaches to describe all kinds of light matter interaction. This is work on Purcell effect in complex photonic structure. I do a bit of applied photonics too. This is a recent patent with Xanadu that we just got accepted about a particular tunable resonator to control the generation of non-classical light. And then a part of my research as part of the research of any physicist should be curiosity-driven research. And this is probably the kind of talk that we are going to see today. Okay, so if you're interested in what I do, you can visit my website. I try to keep it updated as much as possible. Okay, so the outline of my talk will be relatively simple. First, we are going to review the concept of Maxwell Demon because this is a quite famous Gedanken experiment, but not all of you may be familiar with that. Then we will start cooking because I'm Italian, so I like cooking. We will start to gather our ingredients first, okay, just to be on the same page. Then we will present our ignorant Maxwell Demon. It looks clearly ignorant. He has a psi tattoo here on the chest because we're going to talk about quantum stuff, and he has a cape because he will try something heroic. So I decided to put a cape on him, and then we will present the results of our cooking, and finally. There will be for you some take-home messages in one of your chalets here up in the north of Canada. Okay, so but first I would like to thank a number of people who contributed to the work you're going to see. This is Diego, just finished his PhD with me, so he did most of the simulation you're going to see. Giacomo Guarnieri is a recently hired member of our faculty in Pavia. He works in quantum thermodynamics, and you can imagine that his role was important too. And then there is also Matteo Piccolini, who is a postdoc in my group, who contributed to this work as well. Okay, so let's start with the original Gedanken experiment of Maxwell. So in 1867, Maxwell conceived a particular experiment in which we have a room full of a gas in thermal equilibrium. The room is isolated with respect to the environment, and the room is divided in two chambers by a wall. And so the temperature in A and B is identical, so there's an identical statistical distribution of particle, and then there is this tiny aperture on this wall, and a being, Maxwell usually didn't use the word demon, it was introduced by Kelvin later on, but a being is able to open without doing any work, because it is a frictionless lid here, okay, this aperture, and selectively lets a particle pass from one chamber to another. In particular, if the particle has an average speed, has a speed which is larger than the average, it lets the particle pass from A to B, otherwise it doesn't do anything. If a particle in B has a speed which is lower than the average given by the statistical distribution, the demon let the particle from B to A. And so you can understand that after a while, the situation will be the following, that we have all the cold particle, when I say cold, the speed is below the average in A, and the hotter particle in B. And this is an apparent violation of the second law of thermodynamics, because without doing any work, we basically have a heat transfer from cold body to a hotter one. And then, of course, when I have this gradient of temperature, I can use it, okay, and I can perform some work, okay? So now, Of course, there are many objections that one can make to the original idea. Still, this Gedanken experiment kept physicists thinking for many years, and we will see that, and a number of people contributed to understanding what's going on. I want to mention in particular the work of Leo Szilard, because Leo Szilard proposed his own version of Maxwell Demon, which takes the name the Szilard engine. Okay, and I found it particularly interesting because it simplifies very much the situation, and at the same time, he was able to highlight the core aspect of this interesting Gedanken experiment. So, in particular, Szilard imagined just one chamber at the beginning with one particle, in particular one particle gas. And we may question whether this is a good definition or not, but this is not the point. Okay, and the demon observes the position of the particle, and when he knows the position of the particle, basically he constructs a gadget with a massless wall attached here to a load. And of course, he put the load on this side because of the information he got from the position of the particle, such that when this one particle gas expands and undergoes an isothermal expansion, okay, it basically pull up these loads, okay? And so basically, at the end of the day, you have an isothermal expansion from half of the volume to full the volume. So you will extract an energy from the bath, which is kBt log 2. Okay, and this is something you can calculate with just physics 1. Then, this is still an apparent violation of the second law of thermodynamics. Okay, in a different formulation, but it's still the same. And of course, you can imagine now that you will start again, right? And then you continue to extract energy from the bath. Now, let's so recap. So, Maxwell, 1867. Okay, Szilard, 1929, so still after 60 years from the original demonstration. In Szilard in particular, Szilard is very important because he suspected that information had something to do about the possibility of extraction work. And in particular, he suspected that the act of measuring and recording information in a memory could eventually explain the violation. It didn't completely solve the problem, but it gave an important direction. Now, it turns out that the act of measuring or recording, it's not really the point, because either measuring or recording can be done in a reversible way, and therefore they do not imply, okay, heat dissipation. But the work of Landauer, Penrose, and Bennett led Bennett in 1982 basically propose what is acknowledged as one of the best solution to this problem. So the idea is in fact that in order to memorize something, you have to prepare your memory to accept new information. So you have to erase the information that was previously recorded in your memory. And erasing information dissipate heat. It cannot be done reversibly, and you can understand why, because regardless the initial state of your memory, the final state of your memory will be always the same. So this is a clearly irreversible action, okay, which imply dissipating energy, and this was indeed pointed out by Landauer, the famous Landauer principle. So we have to understand that there is a missing thing in the Szilard engine. In fact, basically, before recording information, the demon has to erase its memory, and therefore it dissipates indeed kBt log 2. Okay, because it's erasing a bit of information because there is either left or right the position of the particle. Okay, and as you can see in the entire loop, okay, of the Szilard engine, there is no net gain of energy. Okay, the energy balance is totally zero. Okay, so there is no violation of the second law of quantum of thermodynamics. Okay, now we are not interested here in all the details about this, but if you are, I do really recommend you to read this work. It's a wonderful paper. It's very recent. Okay, Rafael Chavez, Borbarski, and Oliveira Jr. did a wonderful job. This is a paper that if you have a couple of hours time, I really suggest you to read because it's absolutely well written. It's a marvelous paper, very understandable from everybody. It goes through a history of Maxwell Demon, but not only, to classical and quantum version of Maxwell Demons. Beautiful paper, really beautiful, beautiful paper. Well done. Now, the point here, though, is that with Maxwell Demon, which will come back, of course, in a few slides. But the important point is that with Maxwell Demon, we clearly relate information to energy. Okay, because we have information that the demon acquires and a certain amount of energy that the demon can extract, okay, given the information. And this is what we are going to exploit today in our own version, okay? We will exploit this relation. Now, let's start cooking and let's get our ingredients. So we have to understand in this talk, what's information, what's energy, okay? So let's start with information. So information, we are interested in a quantum system, okay? And we are interested in all the information about it, okay? So we are interested in its quantum state. And this state, we know, is described by, in the most general way, a density operator, okay? So the demon has to be able to get information about the quantum state, and the one possible way to do that, and this was highlighted very nicely by Daniel James, okay, here in Toronto, is essentially doing quantum state tomography and measuring the qubits. Okay, and as you can see, this is completely independent of the platform I am considering. Okay, if you're not familiar with a quantum state tomography, very quick review. So, for example, let's be practical, the case of two photons that you can find in Ephraim's lab very easily, okay? So you can perform quantum state tomography by basically performing projective measurements on the photons and, of course, coincidences. And how many measurements do you need to perform? With two photons, you need 16 projective measurements, okay? In general, for n qubits, you need 4 to the n projective measurements. And you need to do so, in a sense, is intuitive, because there are 16 independent elements in your density matrix, which is the representation of the density operator for a given basis. Okay, so always 16 independent matrices. It's a complex matrix here. I'm just showing the real part. Okay. Now, of course, you have to choose wisely these 16 projective measurements, but you cannot do less than that to have a complete description of that. Okay, so there are important details, though, when we talk about measurements that play an important role in what I'm going to tell you in a moment. First important point is that when we say projective measurements, we don't say one click. Okay, we know that because quantum mechanics measurements is a statistical measurements, right? So we are not dealing with one system, but in general, we are dealing with a identical proposed system that we're going to characterize. Okay, and this is very, very important because in general, any experimentalist can tell you that the amount of resources that he has in his lab is finite. Okay, which means that you don't have infinite identically prepared system. You just have a certain number, or simply you have just a certain amount of time to prepare a certain amount of copies of your system. Okay, so in practice you don't get only this, but you get this with uncertainties here, uncertainties which are not related to the uncertainty of your apparatus. Okay, of course they are in part, but even if you have a perfect apparatus, there will be still uncertainty related to the fact that the amount of time you spend measuring is finite. Okay, and so you have only a finite number of copies. It seems trivial, but it will play an important role. Okay, so this is just to talk about information. What is energy in our talk? Okay, so let's consider a quantum system and the Hamiltonian which describe this quantum system. Okay, now let's do this little math work. So we write the quantum system, and you can always do that as a complex decomposition here, where R of J are real. This is outer product of particular states, depending on your state, and we order these weights from the largest elements to the smallest. Okay, and then let's rewrite the Hamiltonian in terms of its eigenstate, okay, and eigenvalues. And again, we do a remodeling here. We basically use kappa. Oh, there is a J here that shouldn't be. We use the kappa from the lowest energy eigenvalue to the largest. Okay. Now, when I do this, I can immediately write a particularly unitary transformation, which basically take the initial state rho and it transforms it in the one with minimum energy. Okay, and this you can verify very easily when you do the math. Okay, it's not difficult. Now, so I can calculate the difference between the initial energy and the lower energy and the final energy. This will be a larger, a number larger of 0. Okay, and this can be calculated because just this is the initial energy, the trace of rho h, so this is just the final energy, the trace of the state that has been transformed by the unitary transformation. And this quantity is called ergotropy. So ergotropy is the largest amount of energy which can be extracted from a quantum state, whatever is the system, through a unitary transformation. And this unitary transformation takes the name of ergotropic unitary. Okay. Yep.
So assuming your state with minimum energy is a pure state, how do you transform from that to a mixed state? You
don't transform it to a mixed state. You will send it to the ground state. If it is a pure state, this Hamiltonian will send it to the ground state through a rotation. You can verify that this is unitary, and then you can apply to it.
I'm just saying, like, if the initial state is a pure state, and you said your rho can be a mixed state.
No. If your initial state is a pure state, rho describe a pure state. Rho describe also a pure state. You can do whatever you want, either pure or mixed. Is that clear? No.
Okay.
So rho describe any kind of state. If this is a pure state, this sum will have only one element. It's fine. It's still okay. I didn't say how many elements you need to put here. Okay. A pure state is a particular kind of mixed state where only one element of this sum is different from 0. Okay, so anyway, then if you want, we can talk about it after. So we can extract this quantity given the fact that we have the Hamiltonian and the information about the state we are considering. Okay, so now this equivalence I show you is basically translated into this. Okay, so we are trying to relate the knowledge of the quantum state that we have in the lab to a certain amount of energy we can extract from it. Okay, and so we are ready to understand our Maxwell Demon. And you can understand that we are going through a kind of Maxwell Demon, right? So our demon start with an Hamiltonian that we give him for free. And we are giving also a certain n copies of the same quantum state, okay? Now the demon has to do something. He has to plan resources. Why? Because he will have to use part of this copy to get information, okay, and part of the copies to get energy from the information he has, okay, and this is, from a certain point of view, is what we do also in the lab, right? We extract information about our state because then we want to use that information, okay, and of course, if we have a limited amount of time in the lab, we have to decide, okay, how long do I have to spend to get information, and how long I have to spend to use it, okay? There's a trade-off, okay. So it will plan the resources, and then it will use the m copies basically to get UST, okay, to do quantum state tomography. And you will see that there is no out here because I am literally consuming my copies or my resources in getting this information. And here I didn't put it in the cartoon, but obviously I have to memorize the results of this information. And so this will be heat dissipated in my environment. Then what do I do? Once I have my state that I do reconstruct, maybe it's not the best state I can get because I use a finite amount of resources, I will calculate, the demon will calculate, because the demon is a quantum demon, so he knows quantum mechanics, will calculate the ergotropic unitary, which of course will depend on the amount of resources is used. And then it will apply the ergotropic unitary to the n minus m particle. The particle undergo the transformation, will be cooled down, and energy will be released. And therefore, we will have extracting energy from this procedure. Okay, there's no paradox here, but the point is that clearly the amount of energy I will be able to extract will depend on the information I have been able to measure. Okay, so which question do you want to? Sorry, yeah.
Should we be worried about the resource cost of applying unitaries?
No, at the moment, no. We assume that we do not spend the resource in applying unitary.
Does that not lead us down to the same kind of trap with Maxwell and so on?
Not really, because the energy already here, when I memorize the information, I'm already dissipating more energy than the ergotropy. So there is no problem in this. Okay, so even if this unitary transformation doesn't require energy, in any case, this ergotropy has been already paid here, because I have to erase the memory of my demon to memorize the information gathered from the measurements. So, which question do we want to answer here? First, does the demon have an efficiency limit? In the sense that, given the amount of information, the amount of copies, yes. Okay, how much energy can he extract? Okay, and you understand that there is a trade-off, because if he uses all the copies to get information, he will have no energy because there are no copies to apply the unitary. But at the same time, if he doesn't measure the particle, in general, when he applies the unitary, he won't get that much energy. Maybe he will even spend the energy because he doesn't have information to construct the gadget. Okay. The second question we want to answer is that what is the impact of the finite resources? Okay, and again, this is very important because we are in a particular historical period in which experimentally we can build very large quantum system, and there is no way we're going to be able to do the tomography of the complete tomography of this system. Okay, so the information that we're going to acquire on the system will be always partial. So we want to understand, so what's the importance between getting information and using it? And finally, we want to answer whether this depends on the way I get information from the state. Is there a way that is more efficient than another in this respect of this Maxwell Demon? So we want to answer this.
Which set of tomographic mechanisms you use or something?
Which approach I use? It can be the set. Okay, so at the moment we're just talking about quantum state tomography. Okay, but maybe also another way to do tomography. Okay, because for the moment we just talk about quantum state tomography, but of course later on I will show you that we can do another way of tomography, which is different. Okay, so let's arrive to the sorry, yeah.
Or I can check that forgets everything. It will dissipate energy on that.
It will dissipate energy, but we assume that the demon has good memory. So we don't assume any dissipation mechanism in the memory of the demon at the moment.
I think the point is that it'll dissipate it, but it won't do useful work from it. If you want to do useful work, then that
Yes, correct. So can you repeat the question?
Setup that you're mentioning is like first, even use part of the states to get information with unitary to dissipate energy from the rest of the state, right? Like, you know.
No. There are n independent copies of my state. They're not correlated with each other. So we use m copies to get information, and the n copies, the other n minus m, can be copies that I even prepare after that. Okay, and I will use them. Okay. But still, even if I prepare after, I will need time to prepare them, right? So the idea is that the number of copies I will be able to prepare is finite in the end.
So all the dissipate energy, to lower the energy. It's to do it unitarily so that you can do work with that energy.
Okay. Exactly. Yeah, maybe. Yeah. Okay, so for the results, we use the toy system, okay, just because we wanted to prove it. We start from a simple system, and we consider an Ising Hamiltonian, okay. Now these are the parameters for your records, but in fact you can work with different parameters. and the results are pretty much have the same qualitative behavior and very slightly different quantitative behavior, but we can talk about this. And then we will use n 2 qubits because this is the smallest system that is also interesting. Okay, there are people that work also with 1 qubit, but at least quantum correlation, we would like to have at least 2 qubits. Okay. And so the idea is that we pick a random state because we don't know what it is. We perform tomography using m copies. Then once we have the state, we calculate the ergotropic unitary, okay, with the procedure I told you. And then we apply the ergotropic unitary to the unknown state, okay? So it's very important that we apply to the unknown state because the demon can do that, okay? And we will extract energy, okay? Now, what happens? Let's try to understand the impact of doing this procedure for at least one simple system with finite resources, okay? If I have an infinite amount of copies, I can get the true state, and I can get the ergotropic unitary, and I can extract the ergotropy from my states, okay? But if I have, for example, only 48 copies, why 48? Because I'm considering 2 qubits, so I imagine that I use 3 copies for each of the 16 projective measurements, okay? Then you see that the result isn't fantastic, okay, in the reconstruction. And therefore, also my ergotropic transformation won't be the ideal, okay? And for sure, if you don't get the ergotropic unitary, you won't be able to send this state in the lowest energy level possible, okay? And therefore, you want to extract the maximum energy from it, okay? And here, indeed, we extract only 30% of what could be extracted, okay? This for a single state, okay? Then if we take 32,000 copy, oh, now you see that they look very similar. The ergotropic unitary looks identical, but still sufficiently good that I will extract 95% of the ergotropy. So which means that if I also calculate fidelity, you see that there is a correlation between fidelity and the ergotropy I can extract, which is obvious because the fidelity from a certain point of view is another measurement of the information with respect to a prior assumption. Fidelity with the unknown state that, of course, in my computer I know. Now, although there is no simple relation between fidelity and ergotropy, okay, it's not just a linear, it's not just proportional. You can see it also from here. Okay. Maxwell Demon, you can see it also right now, can use ergotropy to measure the amount of information that is extracted. And this is certainly true. The more information is extracted, the better will be my unitary, the larger will be the energy I can get from a single system. But of course, our demon is not just interested in information. He wants to use it. He wants to extract energy. So now we define another quantity, which is called ergotropic efficiency. What's the ergotropic efficiency? So if I am n system and total number of copies, and I use m of these copies to get information, the ergotropic efficiency will be the amount of energy I extract at the end of the procedure, which will be basically the ergotropy for having information from m copies times n minus m states copies that are left, divided by the total amount of energy that I would be able to extract if, for some things that I cannot imagine, I can get exactly the ergotropic unitary without doing any measurements. For example, just random. I'm very lucky, I can pick it up. Okay, so I can apply it to all the copies of my system, and this is the maximum energy I can get out of them. Okay. And of course, you can write it also here. Now, the first thing that you want to understand is also, which is a good practice when you find the results like this, is try to understand if there is a limit to this efficiency, right? Because this is what in thermodynamics you do. So what is the limit? The limit, as I mentioned before, happens when Wm, so the ergotropic unitary, is independent on the amount of copy I use, okay? So I assume that I discover, for some reason, I discover a method that with a certain m copies, I'm able to get all the information about my state, okay? And so basically, you get that the ergotropic efficiency limit, or bound, if you want, is this one here, okay? And of course, this depends also on the number of copies I have, okay? So there's no way I can do better than that. Now, let's try now to apply our procedure to the Ising system I described you before. And I pick a random state, okay? And then I try first using, for example, only 10 copies to get information, then I use 20, then I use more, and blah, 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 blah. Okay. What happens? Okay, so first of all, this part is, if you want, interesting in the sense that when I use very few copies, I have none left to apply my unitary, but my unitary will be garbage because I don't have enough information. So I don't extract that much energy. But you see here that for about 10% of the copies, because here there's about 100 copy, okay, I reach a kind of a plateau, okay, which is very counterintuitive if you want. So basically here, I have a good trade-off between having used 100 copies to get my information and then apply to this to 900 that are left. Of course, if I go with larger number of copies to get information, you see that I reach the limit because, of course, if I use more than 30% of my copy, I will basically get all the information I get. So I'm wasting copies, right? Because I'm consuming copies to get more information, but I'm just wasting my time because I should start using the information I want, okay? Now, of course, this is correlated to fidelity, but in a very counterintuitive way, because the fidelity, it measures the information, but it doesn't have really the other part of the problem, using the information, okay? Now, of course, this is done with one state. Maybe I got lucky, and if I pick a different state, I will get a different result, right? So we average on many different states, which is also another, you can also consider it like we are averaging on states, but also on the representation in a sense, okay? So what did we do? We sample over 10,000 states, okay? For each 10,000 states, we consider n equal to 1,000 number of copies. And for each 1,000 number of copies, we consider first a certain amount, about 75 copies for the information, that 128, then 256, then 500 and something, and then we calculate, okay? Yes?
Right, since you said you're going to look at different approaches to tomography, here you're just doing standard 16 measurements?
Yes, absolutely. Yes, yes. And that's the reason I start from here, because I cannot, one copy, I cannot do anything, right? So I will need at least a certain amount of copies.
Right.
Yes, right. Perfect. I just pick a random. Because I have, of course, with 3 copies, I calculate expectation value probabilistically. So they are perfect in the sense that there are no uncertainty except the uncertainty given by the statistic.
How do you tackle that?
Yeah, sure. We consider 50% of them are pure state, 50% are mixed state, and we sample with a uniform distribution depending on the number of zeros on the diagonal elements. You know what? If I could go back, and I will go back, in fact, I would sample these 10,000 states by considering the Shannon entropy of the diagonal and making a uniform distribution. But at that time, we prefer to use 50% pure states because usually when you try to generate a quantum state, you try to generate it nicely and pure, right? So we wanted to have a different, when we want to weight the pure state a little bit more.
Just to make your life harder.
Yes.
I assume you're using maximum likelihood in your reconstruction. If you've got a small number of samples, there are actually big error bars.
Correct. Absolutely.
So what optimizes thing for the maximum likelihood point will probably not maximize the work when you average over the Bayesian distribution.
Well, there are, of course, there is variance here. Okay. Yes.
But I mean, you can come up with a theory that optimizes when averaged over your distributions like the density.
Yeah. So you make a good point. So when I consider quantum state tomography, I consider, of course, quantum state tomography is only what I mentioned, the 16 measurements is only a part of quantum state tomography, because then there is, how do you use the results? So there is also linear inversion, for example, right? So we prefer to use maximum likelihood because it's the most common one, okay? But of course, this has an impact. So absolutely, this result depends on the fact that we also use maximum likelihood, and so it's not obvious that if we use linear inversion, we're exactly the same maximum. The maximum somewhere, obviously, but it's not obvious to me.
No, but I just mean you could. We can just.
Okay, anyway, yeah. Okay, so when we zoom in, I notice, I just make you notice that you can get a negative efficiency. What does it mean, negative efficiency? Because if I perform a horrible reconstruction of my unitary, when I apply the unitary to the state, instead of sending it in a lower energy state, I will send it in a higher energy state. So basically, it will consume even more energy. Okay. Okay. So if we look at the average value and we found that there is a maximum here around 13% of the value used. Okay, of the copy used. So this is the maximum extractable energy. Okay. So basically, it's the compromise that I was telling you before, between using the copies to extract information and then using this NM copy to use this information. And then, of course, you can see from here to here, there's still a lot of space, because we get 65% of what could be theoretically extractable, okay? And of course, we don't know whether, well, this is the limit for this particular procedure that we used, okay? But of course, it means that probably this is not the most efficient approach that we can find, in part, for example, because of what you said about the maximum likelihood, or in part for other reasons. Then what happens? We want to answer it. Yes, almost done. We want to answer it. What happens if we change approach? Okay. So which different approach we change? We still use tomography. We do. We use a slightly different version of tomography. Some of you might remember a talk I gave here about a year ago. So if we consider the density matrix, the density matrix is emission, positive define, and unit trace. And these are three important properties which gives us a very interesting relation between the off-diagonal elements and the diagonal elements. The diagonal elements are those that are directly accessible by measuring on the computational basis. Okay, so we have that the modulus of the complex elements that are off diagonal are capped by the square root of the product of the corresponding diagonal elements. And so we want to exploit this approach, and we construct a different quantum state tomography approach we call threshold quantum state tomography, which I will go very quickly. It works like this. We measure the diagonal elements. Okay, so we consume part of the copy to measure the diagonal elements, and so we are able to understand what is the modulus of the unknown elements that we have in the matrix. So I will set a threshold. How do I set the threshold? There are procedures to choose an optimal threshold, but in general, this threshold can also be chosen on the basis of the amount of time that I have in my lab. Okay, and I will choose to construct a local projection operator corresponding to the off-diagonal elements. Be careful, I cannot construct operators which gives me that element, okay? But just operator which has connected somehow to that elements. But of course, the results of those measurements will give me information about those elements, not exactly the value, but information, which will be then used in the maximum likelihood approach, okay? Not only. We use maximum likelihood estimation, but you can also use other approaches. Now, the advantage of this method is that it allows the demon, for example, in his approach, to decide not only how many copies to use, but also which kind of measurement to do. Because I will be able to understand which are the measurements which contains more information. Okay? So you have to think about the threshold like a limb. Okay, and of course, if you're not very good and you don't have many resources, like me, for example, the bars will be high. I won't perform any measurements, but okay, I will live with that. But if you are like Ephraim, who can go basically like flat because he has a lot of resources, the threshold can be very close to zero. When the threshold is zero, basically I'm doing quantum state tomography as before. Okay, no, all the 16 measurements. Now, just to mention about this threshold quantum state tomography, we verified this on IBM Q, up to 7 qubits. This is what we get from conventional QST. This is what we get from our approach, and we use basically 1,000 measurements instead of 279,000. Measurement, not copy, so the projective measurements, okay, because they are 7 qubits, and we get the same fidelity with the target state. Okay, we get different matrices, but the same fidelity with the target state limited by the machine itself, because this is an experiment, if you want, on a machine. And also, we prepared a GitHub repository with all the documentation so that anybody can use threshold quantum state tomography. This repository was experimentally tested. So I gave it to Fabio Sciarrini in Rome. I told, tell your guys to use this approach. I don't want to interact with you. Let's see if you can use this approach on the basis of the information I gave you. Well, they were able to do that. In fact, recently we published this work in which they perform the reconstruction of a 4-photon GSZ states using threshold quantum state tomography, doing many less measurements than in conventional QST. Okay. So we wanted to try to see that if we use threshold quantum state tomography, we can have a different results. Yes, we expect that because in threshold quantum state tomography, in general, at most you will do the same amount of projective measurements than in QST, but most of the time you will do less, and therefore you will extract information with less measurements. Okay, it's not guaranteed at the beginning how many measurements you're gonna need. Still, it's guaranteed that you're gonna get at most like QST. And so we repeated this on the same states. We repeated this, and we found what we expected. That indeed we have about 13% more of efficiency. Okay, and also in this case we use maximum bracket. So the only things we change here is the kind of projective measurements we did, and then of course we always compare with the same number of copies. Now, what happens if we have a lot of copies? What happens if we increase the number of our resources? Well, the method doesn't matter. We get that as we increase n, for example, we have available 10,000 copies. Of course, we will extract more energy because we have more copies. But also, you see that at a certain moment, when you have infinite resources, really the method is not that different. I will always be able to get the information, okay? Provided that the method guarantees me that I can get that information, right? So there's no problem. But of course, when I have very few resources, the way I use them matters very, very much. Okay, so what happens if we increase qubits? Well, now we tried to do that. Tried why? Because we sampled 10,000 states, but 10,000 states is pretty good for 2 qubits. It's still okay for 3 qubits. We're not sure that for 4 qubits, 10,000 states is sufficient to sample fairly. Okay, we hope it is, but this is very demanding computationally. Okay, at least for the resources we had, we should buy some time on a cluster and then do that properly again. But we still were curious. We get a trend that is kind of expected in the sense that if we consider always 500 number of copies, clearly as we increase the dimension of our system, we see the impact of the finite resources much quicker. Okay, so we extract less energy because we are able to extract less information. Okay, very good. Okay, so we are at the end with our take-home message. First important point, I found Maxwell Demon fascinating, and that's why I recommend you to read that paper, because it's very funny. A Gedanken experiment conceived in 1867 has very much to do, for example, with quantum information theory. It was not even quantum science, but you will see that if you go through it. It's fascinating. Okay, so these Gedanken experiments are extremely powerful. Okay, think about another important Gedanken experiment like the EPR paradox. Okay, so very, very interesting. And another important point is that we basically try to construct our quantum daemon. Okay, and our goal was the idea to understand when to use energy to measure the efficiency with which we extract information to use it. Okay, so unlike only fidelity. And then finally, we found indeed that when there is only partial information that is accessible, it's very important to find the right trade-off. And this is an approach that, if properly generalized, could be very interesting to understand now in dealing with a very large number of quantum systems. How should I plan my resources, since they will be for sure scarce given the dimension? So with this, I thank you for your attention, and I'm happy to answer even more questions if I can.